Hi, I'm Alex Ozdemir, and I'll be giving a short talk about our work at Oakland 2025 titled Volatile and Persistent Memory for zkSNARKs via Algebraic Interactive Proofs. This talk is about building more efficient zero-knowledge proofs, zkSNARKs, that manipulate state, specifically state expressed as a RAM, a random access memory. The previous talk already discussed zkSNARKs, so my background will be brief. A zkSNARK is a special kind of zero-knowledge proof. It is property generic, which means that you can give it any property you want, and it will give you algorithms for creating and verifying private proofs that said property holds for some private data, for example, for data that is encrypted or data that is committed. Abstractly, the property is a function p from secret data to a Boolean, but concretely, each zkSNARK supports a particular programming model and language. So what language is supported by most zkSNARKs? Well, it's a very low-level language. It's not Python, it's not Rust, and it's not even Prolog. Most zkSNARKs support circuits over a finite field. Circuits are very low level, so most programmers use zkSNARKs via a compiler that translates a high-level language down to circuits. Many of these high-level languages use RAM to implement arrays and other data structures. In this work, we improve the performance of zkSNARKs for properties that use RAM. Our approach is to build a base zkSNARK that supports a new programming model, not just circuits. We achieve RAM by compiling it into this new model. I'll make our contributions a bit more clear with a picture. Here is the traditional pipeline for a zkSNARK about RAM. A compiler converts a RAM property into a circuit that goes into the zkSNARK. We propose a new pipeline for zkSNARKs. And this new pipeline, the low-level programming model for the zkSNARK, is different. So to create this pipeline, we created both a zkSNARK for our new model and a compiler that reduces RAM to our model. We find that RAM can be compiled into a smaller computation in our model, giving a faster zkSNARK. In the rest of this short talk, I'll say a few words about our RAM techniques, our new model, and our zkSNARK. So our goal is to prove RAM properties. I'll tell you about the prior work on how to do this. Abstractly, you have a sequence of accesses, writes and reads, of values to addresses. The accesses are ordered by time. And it's hard to show that they are consistent with one another because accesses with equal addresses depend on one another. And when the accesses are ordered by time, these dependencies are not local. So the prior idea is to sort the accesses by address. Now the dependencies are between adjacent accesses. What this prior approach basically does, is it breaks a RAM proof into a permutation proof, an address ordering proof, and a local consistency proof. With this decomposition, it turns out the slow part ends up being the address ordering proof. And it's slow essentially because arithmetic circuits cannot directly do comparisons. They can only add and multiply. So they have to simulate comparisons with addition and multiplication, which is inefficient. Our first insight is realizing that this address ordering is actually too strong. We don't need the accesses to be ordered by address. We just need them to be grouped by address. Because that also ensures that the dependency, that's enough to ensure that the dependencies are local. And so what this grouping property boils down to is checking that the address labels for the groups are unique, that no address is assigned to two different groups. So simplifying a bit, what we essentially want to do is prove that n elements in a finite field, the address labels, are unique. And the verifier is a circuit that can only add and multiply. So how can you do this? Well, one approach is to have the verifier do a sort, which of course requires a big circuit, both because sorting requires a circuit of superlinear size and because sorting uses comparisons, which, as I said, are expensive. There's also a better circuit that doesn't do sorting, but still does a bunch of comparisons, so it's still pretty inefficient. But what we found is a new solution, a new way of doing this, that is simple, is beautiful, and it is concretely efficient. In fact, it has strictly linear cost, and the constant is just 4. But to see our solution, you'll have to read the paper, because this talk is too short for it. What I do want to do right now is give you one key insight that we had that allowed us to find this solution. Our insight, this is the second insight in this talk, was realizing that we should change the model of computation by allowing for randomness in our circuits. In a bit more detail, in the prior model for zkSNARKs, arithmetic circuits, the operations that you were allowed to do was take a public input, a private input, do a multiplication, do an addition, or assert inequality. And what we add is just one new operation, sampling a random input, in order to capture some informal notion of randomized circuits. More precisely, we formally define our model as algebraic interactive proofs, or AIPs for short. As the name suggests, AIPs are connection to complexity theory. And our formalization captures details such as the fact that the secret inputs and the random inputs can depend on one another. They might enter the circuit in multiple rounds, just like the rounds of an interactive proof. So one of our contributions after we formalize this model is building a zkSNARK for our model. We show that you can convert any AIP for some property P into a zkSNARK for the same property. This zkSNARK is essentially a formalization of an idea called verifier randomness that has been in folklore, unformalized, for a few years. And even better, our construction that implements this zkSNARK is extremely efficient. It's just as efficient as the best zkSNARKs for circuits, but it's for a stronger programming model, so it's more powerful. So anyways, using our new RAM constructions and new zkSNARK, we put them together and are able to build a number of efficient zkSNARKs for different kinds of RAM. The first kind of RAM we study is persistent RAM, in which the initial and final state of the RAM are represented by hashes. The proof shows that some transition between those RAM states is correct. Here, we obtain asymptotic speedups, and we also obtain a concrete speedup that beats the state of the art by a factor of 50. For volatile RAM, which is a special case of RAM where the initial state is zeroed and the final state is ignored, the only thing that matters is the output of the program that runs on the RAM. We get an asymptotic speedup for large RAMs, but the concrete speedup is rather small, say only 33% for a 64-bit address space. And the reason that we don't do quite as well here is that this special case, volatile RAM, was already pretty well optimized. So the state of the art is just better. And then finally, we study a different special case, sparse persistent RAM, which is once again a situation where the RAM is hashed, but most of the cells are 0. So it's kind of like Swiss cheese. The RAM is missing a bunch of spots. And here we didn't implement our approach, but we did build some cost models, and according to our cost models, we get a big asymptotic speedup and an even bigger concrete speedup than we get for normal persistent RAM. So that's all I have time for today. To summarize, in our paper, we construct better zkSNARKs for RAM properties. We do this using a new programming pipeline for zkSNARKs built around AIPs, algebraic interactive proofs, instead of circuits. We contribute new reductions from RAM to AIPs and also the first zkSNARK for AIPs. If you want to learn more, then you can read our paper where you'll find a bunch of details on a whole bunch of different things. One of the things that you can learn about is how we prove uniqueness using a very simple, very elegant AIP. You can also learn more about the details of the different kinds of RAM we study and why those different kinds of RAM are important. You can learn how we define precisely the notion of security for a zkSNARK for AIPs. You can learn about how we construct such a zkSNARK, starting from Grot16, which is one of the most efficient elliptic curve-based zkSNARKs for circuits. And then, of course, you can learn about our experimental results. The last thing I want to say is that in this paper, what we essentially do is we build a new pipeline, and we apply this pipeline for zkSNARKs. We apply it to RAM properties. But we don't think that this pipeline is just useful for RAM. In fact, we think that this pipeline is going to be useful for a whole bunch of other kinds of properties as well. And in fact, this year at Oakland, in the talk right before this one during the conference, there was a paper about doing signature verification for legacy signature schemes like ECDSA, EDDSA, using zkSNARKs in order to build anonymous credentials and things like that. And that paper also uses exactly the same pipeline, but it doesn't apply that pipeline to RAM, it applies that pipeline to signature verification instead, and it gets big speedups for signature verification properties. So one thing that we think is very exciting about this work is that we imagine that our pipeline is not just going to be good for RAM, it's not just going to be good for signatures, it's probably going to be good for a lot of other things too. And if you're working on a zkSNARK for some property, I would encourage you to think about how randomness might be helpful for that, and maybe even reach out to us, where we'd be happy to help you figure out whether randomness can help your problem. Thank you very much.